Hello, beautiful humans. Welcome back. I hope you all had a great break and got a chance to kind of rest and recuperate. I'm pretty excited to see you again because we are actually going to be starting on probability. So for those of you who already watched the Khan Academy and did some of those multiple choice questions, you are on track. Anybody who didn't, that is your starting place for your first lesson, is to go through and do those Khan Academy videos, readings, and multiple choice. It shouldn't take you more than a class period. So we're actually going to be doing daily videos for the rest of this semester, which means that you're going to go through at your own pace. If you need to pause and go back, you can do that. If you feel like you get it on the first try and you want to go straight to some practice problems, you have that option. So this is really self-driven because some of you want to go over things more slowly. Some of you would prefer to go and try some practice problems and see how you do. Today we're going to be talking about mutually exclusive events. So our goal is to explain why two events are or are not mutually exclusive. And we're going to start out simply with what are we going to learn? We're going to learn why some events might be called mutually exclusive and others not. So mutually means together, exclusive means they can't be in the same place at the same time, right? So mutually exclusive basically has to do with things where you can only be one thing at a time. So for example, we have here different genres of music. So we're imagining, I don't know if any of you are into like vinyl records. It's not a thing that I'm into, but some people really get into it. They feel like, you listen to music online and it's not quite the same good sound as you get from playing an actual record. And so when you walk into a record store, everything is in its own category. So you can buy a pop record, you could buy a hip hop record, you can buy a jazz record, but they're not going to have jazz and classical, right? It's all going to be in its own category. And so if we want to find the probability, for example, of any record in the store being a jazz record, we're going to take the total number of jazz records for sale, which in this one is 431, divided by all the records in the store, 2,105, and that's going to be our probability. So now in this example, because an album can only be classified by a single genre, we say that the genres are mutually exclusive, right? And our definition, which I'm going to encourage you to take notes on this video, so this is important, mutually exclusive, also called disjoint events, cannot occur at the same time. Only one of them can happen at the same time. So another example of mutually exclusive events would be, what's the probability that I am in my house right now versus the probability that I am at school right now, right? If you're physically in your house, you cannot also be physically in school or physically at the school building. Although I realize that right now, we're all in school at home. We use Venn diagrams a lot. Venn diagrams can be used to represent probabilities in a visual form. They often use circles or ovals to represent events, and the portions where the graphs overlap is the intersection of the two events and is represented by this notation that you're seeing here. This is A intersects B. So anytime that we see A intersects B, with this, it almost looks like an N. We know that we're only looking at the probability that both of these two things are happening at the same time. Like this. When we draw our Venn diagram, A intersects B is only the part in the middle. If we have mutually exclusive events, they can't occur at the same time, right? We can't both be in our houses and in our classrooms, right? So we say that those events are mutually exclusive and there would be no intersection of the two events. So when we draw our Venn diagram, it's actually going to look like this, where we have two separate circles that never touch. So we can think about this with dice. When you take the APS test, they say number cubes, which I've never heard anybody say, roll a number cube. But If they're thinking about rolling a die that has sides 1 through 6, there are a few possible options. So they've given you some options, and we're going to look at these to decide which two events are mutually exclusive. So we have odd numbers. The odd numbers would be 1, 3, and 5. Then prime numbers, which are 2, 3, and 5, and even numbers 2, 4, and 6. And we want to calculate two different things. We want to find the probability of A intersects B. So that's the probability of odd numbers intersects prime numbers, and then the probability of odd numbers intersects even numbers. For the first one, we are looking at this 1, 3, and 5. And we're seeing if there is any number here that is also in event B, 2, 3, and 5. And I can see pretty clearly for this one that 1 is not in this group, but we have 3 here, 3 here, and we have 5 here and 5 here, which means that there are two numbers that are in both of these. And because there are 6 numbers on a dice, we're going to say 2 divided by 6 equals 1/3, or if we do in decimals, 0.3333. That's our probability of A intersects B. Now I want to look at my probability of A intersects C. So take a moment for yourself. Are there any overlaps between event A and event C? Well, no, right? I don't see any numbers 1, 3, and 5 that are also in this 2, 4, and 6, which means that we're going to say that A intersects C is 0 out of 6, which equals 0. So if we're thinking about our Venn diagram, there is no overlap between odd numbers and even numbers. So those are two separate circles. And suddenly we realize they're mutually exclusive. Anytime that we see these two events have a 0 probability of both existing at the same time, that's mutually exclusive. So let's look at another example. We're going to look at an example about people's preferences for superpowers. You might remember this from earlier this year. So we have high school students. We ask them, if you had to choose a superpower, what would it be? And they can choose from a number of options for superpowers. And then a separate question, which of the following would you prefer to describe you? Famous, happy, healthy, rich. And then we made a two-way table. So remember that our two-way tables have one categorical variable and another categorical variable. And we're going to use this to find some probabilities. So the first one, what's the probability that a randomly selected student chose to be happy? Well, we're going to look in my happy column. And in this column, the total number of people that chose to be happy is 265. And I'll divide by the grand total, 433, which is going to give me 0.612. That's one probability. Now let's try another one. What's the probability that a randomly selected student chose both to be happy and to freeze time? Now we know this. We can do this by looking at the table. Okay, here's happy, here's freeze time. These are the people who wanted both. We need to also know how to write this in probability notation. And that's what we have here. P happy intersects freeze time. So that's a 63. And we still divide by the total people we asked, which is 433, to get our probability. So these ones are not mutually exclusive because there is some overlap between wanting to be happy and wanting to freeze time on that Venn diagram. We call it a joint probability, right? It's a probability of the intersection of the events happy and freeze time, like that. Now this example is another joint probability question. What's the probability that somebody is famous and uses telepathy? Well, for this example, I'm noticing famous and telepathy gives me 0. So when I divide it, it's going to be 0 divided by 433 equals 0. And because no students chose to be both famous and telepathic, the two events are mutually exclusive or disjoint. So our takeaways for today. The joint probability is the probability of the intersection of two events, which we write with this symbol. And two events are mutually exclusive if they cannot occur at the same time. If two events are mutually exclusive, then the probability of their intersection is 0. All right, that is it for today. You're going to go through this video if you need to look at it more. And otherwise, go ahead and do the practice problems that are posted on Schoology. Bye, everyone.